Hello everyone, welcome back to Z Physics. Today we're going to be carrying on solving the 2020 PAT Oxford entrance exam. We're going to be solving the physics questions only in this video, and this is part 3 of a series. So if you're looking for some of the previous question, have a look at the links in the description. Before we get started properly as well, just a little disclaimer that these are not official solutions, and I've provided a link to the official paper and the Oxford website for the PAT entrance examination. Well, let's get started with question 23. Monochromatic beam of light travels through air of refractive index Na, and it strikes a liquid of refractive index N1 at an angle of incidence theta, as shown in the figure below. The bottom of the tank, which contains the liquid, is a plane mirror at an angle phi to the horizontal. So this is really interesting. It strikes this boundary here, so that we're going to have one refraction here, then we're going to have a reflection somewhere here, then we're going to have yet another refraction. So this will be a 3-part problem in a way. Beyond a certain value of theta, the light no longer leaves the tank after the first reflection in the mirror. Find the value of theta for this case, and we're given some values for the angle of the incline, Na being the refractive index of air, which is 1, and the refractive index of this liquid here, which is 4/3. And we can use this large diagram to draw a ray diagram. Now, the first thing that I really encourage you guys to do would be to draw your own ray diagram to really get a feel for what is happening in this problem. Let's do this. So first of all, as the ray is going into the tank, it is going to refract towards the first normal. Let's say that this here is our first normal. I'm going to call this angle theta 2. As the ray goes on, it is going to get reflected. So those two angles are going to be equal with respect to this inclined plane. This second normal will be offset by 10 degrees from the initial normal, because the angle of the inclined plane is 10 degrees. When the ray gets reflected here, it will get refracted once again before it leaves. Now the question is, can we find an angle theta which is going to influence theta 2, which will influence this reflection angle, which will influence this angle theta 3, such that the ray will remain in the original boundary. So we'll be looking for the critical angle such that the ray remains along this line here. Next step, now that we know roughly what is happening in this question, would be to write some fundamental equations which will help us determine the angle theta. Now, the law of refraction, which is also known as Snell's law, says that the refractive index multiplied by the sine of the angle is a constant. In other words, translating that into mathematics, we get that the original refractive index, which is the refractive index of air, times sine theta will be equal to N1 times the angle of refraction, which is sine theta 2. Because ultimately we're looking for theta, I'm going to rearrange this equation for sine theta. So sine theta will be equal to N1 multiplied by sine theta 2 and divided by Na, which is 1, and sine theta will be equal to, actually let's just rearrange that for theta. Theta will be equal to the inverse sine of N1 sine theta 2 divided by Na. Now notice that in this equation we're actually given the value of N1, that's 4/3. We're given the value of Na, that's just 1. So all we need to do is find this angle in degrees, and we can really easily find our angle theta. Now I'm going to take a backwards approach. I'm going to find my theta 3 first of all, our critical angle. Then I'm going to see if I can use geometry to work my way back and find theta 2. Well, let's do this. We can actually find theta 3 relatively easily using our understanding of the critical angle. Let's apply Snell's law once again for this boundary. What you're going to find is that n1 times sine of theta 3, let's say the theta 3 will be that critical angle, will be equal to the refractive index of air, NA, and if the ray is trapped along this boundary, the angle to the normal will be equal to 90 degrees. So this means that the sine of our critical angle will be equal to NA sine of 90 divided by n1, so the sine of the critical angle, now NA is 1, sine 90 is 1, is going to be 1 over the refractive index of the original substance, which is 4/3. If you're doing OCR physics by any chance for your A levels, there's a formula. I'll just write this over here on the sine that says that sine of the critical angle is 1 over n. We've essentially just derived that formula from scratch. Anyways, we can substitute or we can just directly input some values and find theta 3 to be equal to the inverse sine of 1 over 4/3. Just please be careful with the brackets over here, and let's give it quite a bit of significance to avoid any errors further on. So it'd be 48.59 degrees. So we have managed to find our theta 3 to be 48.59 degrees. Now let's see whether we can work backwards and figure out what our theta 2 will be if the reflection occurs at an inclined plane of 10 degrees. Now that we know that theta 3 is 48.95, let me talk you through how to find theta 2. There may be an easier way which I've not spotted. If that's the case, please let me know. Now, first of all, theta 3 and this angle here must add up to 90 degrees because this is a normal right here to this surface. This means that the angle that I'm pointing at is 41.41. The next normal to this surface is not normal to the surface above. So the angle up here is no longer going to be 90 degrees, but it's going to be 80 degrees because the surface below has been inclined by 10 degrees. This means that, well, these angles have to add up to 180 in the following triangle, meaning that the angle here will be 58.59 degrees. With the law of reflection, the angle to this normal will also be 58.59 degrees. Of course, because this is a normal to the lower surface, the following angle here will be equal to 31.41. Now that we're dealing with the normal to the first surface along this line, the angle here will no longer, it's going to be 90 degrees, and it's going to be 10 degrees more because the surface dips a further 10 degrees. So that's going to be 100 degrees. Finally, in our final triangle, just over here, the angles need to add up to 180 degrees, meaning that our theta 2 will be 180 minus 100 minus 31.41, giving us a value of theta 2 to be 48.59 degrees, which is actually equal to theta 3. If you've noticed an easier way of doing this, this wasn't completely obvious to me. It would have been obvious if those lines were parallel. However, if I've missed something in geometry, do let me know. Now that we have found that theta 2 is equal to 48.59 degrees, let's substitute that back into our original refraction equation which we derived at the beginning of this video. We derived that theta is equal to the inverse sine of n1 sine theta 2 divided by NA. So let's plug in some numbers and put them into a calculator. Theta will be equal to the inverse sine of n1, which is 4/3 or 4/3, multiplied by the sine of theta 2. So that's the sine of 48.59, and we're going to be dividing that by NA. Well, that's just 1. Inputting this into a scientific calculator, the angle is going to be right on the limit of what's possible, so it's going to be 89.8 degrees for the angle theta. Question 25, the last physics question of this paper. So in Millikan's oil drop experiment shown below, we have a spherical oil drop. We're given the charge, which is positive. It has a radius r and a density given by rho oil. So initially the switch is open, so this means that there's no electrical forces and the drop is falling with terminal velocity Vt. We're given the density of air and the viscosity, which is given by eta, which is this symbol over here. So we now measure its terminal velocity, write down an equation that relates all the forces on the drop while it falls at terminal velocity. And we're given a hint that the drag force is given by the following expression, given the viscosity as well, and the drop experiences a buoyant force of upthrust Fb equal to the weight of the air displaced by the drop. Okay, so the first one is essentially looking for the resultant force. At the terminal velocity, all of the forces are going to be balanced, so there's not going to be any net force. There are essentially 3 forces acting on the drop. First off, the weight of the drop given by the mass of the drop times g is acting downwards. We're going to have a drag force and a buoyant force, and they are going to be balanced. So the mass of the drop times g, this is the weight of the drop, will be equal to the drag force plus the buoyant force. Now, because we're given all of these viscosities, and throughout this problem I'm going to be using quite a lot that the mass in general is given by density times volume. This means that we can represent the mass of the drop as the density of the drop times the volume. So the density is given by the density of the drop, rho drop, times 4/3 pi r cubed, where this is the radius, times g. This is going to be equal to the drag force, which is given, of course, over here, 6 pi times the viscosity times r times the terminal velocity, plus, now remember, the buoyant force by Archimedes' principle is equal to the weight of the air displaced. Now this will be the mass of the air times g. The mass of the air will be given by the density of the air times the volume displaced, which will also be equal to 4/3 pi r cubed, assuming of course that the drop is spherical, times g. Now in part B, the switch is now closed and we've applied the uniform electric field E to the drop. Now, because the drop is positive and the positive plate is here, this means that the ball will get attracted upwards. So this means that there's going to be an upward electrical force. Now the buoyant force will also still be there, and we're also going to have the weight acting downwards. Now because the ball is, or the drop is now stationary, so now it becomes stationary, there's no longer going to be a drag force. So let's just write down an equation relating the forces on the drop. Okay, so because it's stationary, all the forces have to be balanced again. So the mg of the drop, let's be quite accurate, m drop times g will be equal to the buoyant force plus the electrical force, like that. And we've already found the difference between the buoyant force and the weight, or the difference between the weight and the buoyant force. So let's do that again. So m drop times g minus fb will be equal to the electrical force, which I've just called fe. Now this difference here we've just derived, this is just here, so I'm literally just going to copy this down, and what I'm going to get is that 4/3 pi r cubed and times g will be equal to the density of the drop minus the density of the air, and that's going to equal the electrical force. Now the electrical force is given by E times Q. The reason for that is because in general, I can write it over here somewhere on the side, the electric field is the force per unit charge. Therefore, the electrical force will be equal to E times Q. So this will be equal to E times Q. And this is an equation for the balance of those forces. Let's tackle part C. Now part C is asking us to derive an equation for Q which does not depend on the radius r. Quite often when part A and part B are asking us to derive a couple of equations, part C will quite often be asking us to combine them in some way, and I think this is the case in this question. Well, let's have a look. So derive an equation for Q which does not depend on the radius r. So this first equation, 4 pi r cubed g times the difference in density is equal to EQ. Let's just rearrange that for Q. So Q will be equal to 4/3 pi r cubed g times rho of the drop, take away the density of the air, and what we're going to be doing is dividing that by the electric field. Now all we need to do is to find an equation for R which is dependent on some of the other quantities. Well, luckily for us, just over here in the previous part of the question, we said that 4/3 pi r cubed times g times the density of the drop minus the density of the air is equal to 6 pi times the viscosity times r times vt. Well, we can actually find an expression for r from this equation and then sub that in to part C. Well, let's do this. So first off, we're going to cancel out a factor of r. So what we're left with is 4/3 pi r cubed, r squared, sorry, times g times the density of the drop, take away the density of the air, will be equal to 6 pi times the viscosity times vt, which is the terminal velocity. Notice that this here is just a subscript for terminal velocities, not v times t. Maybe I should be just a little bit more clear by doing that. Okay, well, now that we have this, we can rearrange for r squared, and what we're going to get is that r squared will be equal to 3 times 6 times pi times nu times vt divided by 4 times pi times g times rho drop, take away rho air. Okay, now we can cancel all the pi's, be gone pi's. We can do some cancellations over here. For instance, this here will become a 2 and this here will become a 3. So r will be equal to the square root of 3 times 3 is 9 times nu. Let's not write the multiplication sign actually, so it's going to be 9 nu Vt, and that's going to be divided by 2g times the density of the drop, take away the density of the air. Okay, excellent. So all we need to do is take this expression for r and raise that to the power of 3 and substitute that back into the original equation. If we plug this expression, which is r square rooted, remember square root is essentially this quantity raised to the power of a half. So if we raise something which is already to the power of a half and then we cube it, what we're going to get is this expression raised to the power of 3 halves. So what I'm going to get for our charge q is going to be 4/3 times pi times this expression, which is 9 times the viscosity times v subscript t divided by 2g, the density of the drop, take away the density of the air, like so, and that's raised to the power of 3 halves. And so this is simply our r cubed, and then we're going to multiply this by g, and then by the density of the drop, take away the density of the air. And what we need to do finally is just to divide by E. Notice that at this stage we've already successfully answered the question. We have an equation for Q which is not in terms of the radius, and when this experiment was performed, this was actually one of the trickiest bits, because it was incredibly hard to actually measure the radius of a drop accurately. Now, what I've done then is just tidied the expression up, which may or may not score you marks. I personally doubt it, because Q is, we already have an equation for Q in terms of E, but if you have some time, pretty unlikely, but if you have a little bit of extra time to just tidy this expression up, all I've done here in the remaining 2 lines is essentially divided this factor of 1 by this factor of 3 halves, and what I get is a factor of g rho drop minus rho air to the power of minus 2. I've also put this factor of 2 to the power of 3 over 2 up here, and then finally I've just essentially brought this factor of which is raised to a negative power at the bottom of the fraction together with this factor, leaving me with a final expression for Q, not in terms of the radius, to be 4/3 pi 9 times the viscosity multiplied by the terminal velocity raised to the power of 3 over 2 divided by 2 raised to the power of 3 over 2 times g times the difference in densities square rooted. Okay, folks, well, this was a really interesting question. I really enjoyed working through this. Look at all this work going through this. Hopefully you've enjoyed this. Hopefully you found this useful. Good luck in your preparation. If you spot any mistakes in my working, please get in touch. Thank you very much for watching, and I'll see you in the next video.